we are to ruin. Of course, it's also going to depend on the loading factor, theta, and these are the things we believe we have control over. We might be interested, well, time is something we know we're looking for a certain fixed time. U we can control how much is initial surplus, theta we can control, which is how much money we're going to charge. So we might want to see how the probability of ultimate ruin, or probability of ruin in finite time, depends on the loading factor, the U and the time. Now, it'd be difficult to do this in general because we've got lots of distributions and lots of expected payouts and lots of numbers of claims. So, but I can do some things. I'm going to make the assumption that it's exponential, which is a quite strong assumption. I'm going to make the assumption it has mean 1, which is a very weak assumption because all it says is that I'm measuring my monetary units in mean claim sizes. So the picture I show doesn't really depend on the mean 1, because 1 could be £2,552. But all I'm knowing is 1 unit, 2 units, 3 units. So when we think about U, we're thinking about how many times the average claim do we keep in reserve. And again, I'm going to have the Poisson parameter, and I'm going to make the number of claims 1 claim per unit time. And that isn't a strong assumption either for my investigation, because all I'm saying is my unit of time is defined to be the length of time before I get 1 claim. So if I get 1 claim per hour, then I'm talking about hours. If I get 1 claim per month, then I'm talking about months. If I get 1 claim every 7.5 days, I'm talking about 7.5 days. So all I have to realise here, T in my plots is going to be the number of, or at a point time T, that's the expected claim, number of claims up to that point. And I've just done some plots, and I'll explain how I got these plots right at the end of the course because I got them by simulation. But what you need to do is just to understand the way that these behave, the shapes of them. So here I've got a plot. What is this the plot of? This is time along the bottom. This is the probability of ruin. And this is the initial surplus is 15, and the loading factor is 0.1. And what we can see here, as you expect, and the pattern is the probability of ruin starts with a little bit where you've got some reserve. So you'll see you've got some reserve. So the probability of ruin very early on is 0 because we've got some reserve. Then it kicks up very quickly because there's a chance now of getting a few claims that wipe away our reserve. So after an initial point here where it doesn't go up, it shoots up quite quickly because there is a chance of lots of claims before we build up enough money. But over time, if we haven't been ruined by a particular point in time, the probability of ruin further, it does increase, but it increases slower because if we've made it to 200 time units, then we probably built up enough reserve to pay to cover the claims that come in. So that's the general shape of these curves, is that you've got a bit here that's flat, and then up, and then it flattens off. And we know, well, 2 things we know. For an exponential distribution, I can work out, using the formula on the previous page, the probability of ultimate ruin. So this, we know the asymptote. This will, at some stage, at time infinity, come to this line. And also, we can assess the quality of the Lumberg's inequality. So the second line, the first line is the exact result for the exponential, the first horizontal line. The second line is the Lumberg's inequality. So I think I've said everything about that. Clearly, as time goes on, it's an increasing function of t. After an initial bit, it increases, it goes up very quickly, and then it increases slower, and then it approaches this line, the probability probability of ruin, was it 15? So now I'm going to just do a little experiment and say, what happens if I change U? So if we change, so the only thing I've changed is U. So the main thing that happens, well, there's two things you should know. As we expect, the probability of ruin decreases as U increases, which is what we'd expect. I've probably got this here at the bottom. So the probability of U decreases, of ruin decreases as U increases. They all have the same sort of S shape. But what happens, of course, if you've got more reserve, then it's a more pronounced. You don't get ruined for a long time. The probability of ruin stays very low to start with because you've got this reserve. So here we've got 25, equivalent of 25 average claims we can afford before we get any money. So that should be that we can survive. We're getting on average one claim a day, so on average, without any money coming in, we could survive on 25 days on average. And we have money coming in, so you can see here. Whereas here we could survive 15 days on average, because we've only got 15 average claims amounts, and remember there's on average one claim per time unit. And then they have the same shape, and they're all asymptotic. We could have worked it out, we might like to just check. We can work out the asymptotes for each of these. There we go. So it gives us an idea. If we have a decision that we want to keep the probability of ruin at 5%, and we want to keep our portfolio for 10 days, for 200 time units, then it gives us an idea, reading off here, about what our initial surplus should be if we wanted to keep theta at 0.1. It would be 25, whereas if we were only wanting to do it for 100 days, we need only start with 20. If we wanted a lower probability of ruin, we probably need an even higher U, so another U down here. So my final curve, can I get it all on, is this time I've kept the initial surplus fixed at 15, and I've changed the premium loading factors. So clearly, as you increase the premium loading factor, you're getting more money in. So the probability of ultimate ruin is going to decrease with increasing theta. Clearly, again, we've got the same pattern that, of course, as T increases, ruin increases. Again, they all have this S shape, but what happens now is, unlike the U, they all start when we change U, you go back here, and change U, a bit down here, can you see that? It was quite a bit different, because we had money in reserve. Here, they're very similar at the beginning, because the amount of money coming in isn't the important thing here. We have 15 units of money average to start with, but it doesn't matter here. The amount of money coming in is really not an issue right at the beginning. It's the number of claims going out. So they have a very similar shape at the bottom here, because whether we're getting 30%, 20% or 10% more money in the first few days, it doesn't really affect the ruin. But then, of course, after you've not been ruined for a while, then the ruin increases greatly if you're not getting much money in. So they all have the same shape, and the final thing is, so for small values of t, the curve increase rapidly. So if you've got large amounts of money coming in, once it starts to kick in, you can see here, it increases quite quickly. Okay, so that's the end of ruin theory. So what have we done in ruin theory? Leave a few minutes to go through these solutions to the past test. So the basic is, I introduced the idea of, we haven't done that much really, we've introduced the idea of a surplus process, so it took a few lectures to build up to this process, and the definition of this process, We then define 4 ruin probabilities, all very difficult to calculate without using simulation. For this one here, we introduced Bloomberg's inequality, which requires the adjustment coefficient. So there was a bit of solving equations to get R. And then we got some examples about how we might use this to decide, choose, perhaps find an upper bound on this, or choose the premium loading factor. Sometimes we can't find R, so I gave you an upper bound on R, a way of finding an upper bound on R. And we looked at some plots of this thing. So that's what we've done with 2.5 lectures. As I say, we'll come back. This is the last lecture I've given for a while, but I will come back at the end and do simulation. And the beauty of I like simulation is it really can be a revision for various. It will be a revision for ruin, it will be a revision for risk. It'll also be a bit of a revision for some things you haven't read. Okay, so hopefully you've seen your results for the class test, which are on Blackboard. What I want to do in the next 10 minutes, or if you want to stay on a few minutes extra, 15 at most, is just to go through the answers. And the class test is worth 5%, so it's not really a big deal. It's really for you to assess where you are in the in your revision and keeping on top of the lecture notes. So I'm sorry I can't give you all the solutions out and back, so hopefully you can remember what answer you gave, and then when I show you the right answer, you'll see why you got it wrong. I did have some feedback on the number of answers, which ones you found difficult, but I haven't had a chance to look at that, so I'm grateful for it. So, and you see that. Hopefully you can have at least remember what you did. I think question 1 was got right by most people, so I won't spend much time. Just if you don't understand what immediately the solution, and maybe stop and ask. So this is an integration by course. We can see immediately that this looks like a Pareto. The parameter is going to be lambda and 3. So because this is alpha plus 1, so we've got 1 too many lambda here, so it's going to be a lambda. And what's missing? Well, there's a 3 missing here, but there is a 6, so this is 2 lambda. And I don't think too many people struggle with that one. The third cumulant of an exponential distribution, well, there's 2 ways of doing that. The easier way is we know the coefficient of skewness of an exponential distribution is 2, so that's the quick way. The coefficient of skewness, as you look in the table, is 2, and we know that that's going to be the third central moment, or the third cumulant over the second cumulant to the 3 over 2. We know that this is going to be, we know that this is lambda, so that with a bit of work we can show that it's actually C. So the main thing is, alternatively, we could write down, if you wanted to, the cumulant generating function, just to remind you. If you go to the tables, you'll find the moment generating function of an exponential is this. So the cumulant generating function is that, and then I differentiated 3 times, and we'll get the answer C. I don't want to spend time differentiating this 3 times, but the main thing is, did you forget what the cumulant generating function is? It's the log of the moment generating function. So this is the sort of that was a trick. This is the correct way to do it. Differentiate this 3 times and set t equal to 0. The next one, we know that the collective risk, the mean of a collective risk, is going to be the expected number of claims times the expected claim size. So we're told that this is 4. We need this. Now the main thing here is to remember that insurance, the negative binomial will be using the type 2 one, so this is going to be alpha Q over P. So alpha, so that is going to be, what is that? That's 4 times 0.8 over 0.2. So that's 4 times 4 times 4. 16. Oh no, there's a 6, sorry. Alpha was 6. So that's 4 times 4 times 6, which is 96. So there are 2 revision things there to remember. Is this equation, which is in the tables, and we're never going to, I promise you, you will never have the type 1 negative binomial in this course. It's always type 2. So you might have got this wrong if you looked at the wrong type. We'll see, sorry, 4 is a result that is worth learning. You could have derived it, but a gamma mixture of exponentials is Pareto. Just a fact. If you wanted to, you could have written down the exponential distribution, the gamma distribution, multiplied them together, integrated out the lambda, and then you would have seen it's a Pareto. But that's again just a fact that you perhaps remember. If it had been a gamma mixtures of gammas, with the first parameter of the gamma not equal to 1, then it would have been a generalized Pareto. But in this case, it's a Pareto. The next one, well again, we've talked a lot about tail decay. And again, the answer is Pareto. Remember, Pareto had a 1 over x to the alpha decay, where the others are e to the minus x to the gamma decay. So, and we know that, or you should know that reciprocal decay is slower. So, one thing was to remember, what do we mean by heavier tail? And then we had a long discussion over about 2 or 3 lectures about tail decay. So, the Pareto is the right one there. The exponential, as we discussed, is probably not wonderful for modelling losses because it's got too light decay. Again, the rival with a gamma greater than 1 is also too light. So if gamma is greater than, if gamma equals 1, we have the exponential. If gamma is greater than 1, we have something that's even lighter. Remember, in insurance, we do intend to have these extreme events. This one just required some memorization of the definition and a bit of how to integrate. So, the coefficient of variation is the standard deviation of x divided by the expectation of x. So, E of x is going to be the integral of 2.5 x to the 2.5 dx. And E of x squared is going to be the integral of 2.5 e to the minus 1.5 dx. So I'm multiplying this one through by x, and this one through by x squared. So that integral, you have to notice it's going from 1 to infinity, and what you get here, you get 2.5 over 1.5, and here you get 2.5 over 0.5. For those integrals. So if I don't know again how much I want to go on, but 2.5 over 0.5 minus 2.5 over 1.5 squared, square rooted, divided through by 2.5 over 1.5. And with a bit of work, it turns out to be A. So, I mean, again, you can one thing you can do is award yourself half marks on a pass test, because you really, as I say, it's to judge how far you're getting. So if if you remembered this, but made a slip here, or did this, but made a slip here, you'd probably do. I sort of know what's going on. So that was, so question 7 was about goodness of fit. So the first one, you had to ask, are they right or wrong? Well, the first thing is you need to know, if you're doing goodness of fit test, how many degrees of freedom do you have? Well, you have the number of parameters minus plus 1. So the number of groups minus the number of parameters minus 1. So for the Pareto, we would have 13 degrees of freedom, 3 parameters and an extra 1, 70 minus 3 minus 4 is 13. We would have 14 for the Pareto and 15 for the exponential. So this is wrong. It should be 14 degrees of freedom. It should be 13 degrees of freedom for a generalized Pareto. The exponential fits these data better than the Pareto. Well, clearly the Pareto fits a lot better. This is much smaller, even allowing the degrees of freedom. It turns out that you wouldn't have to do anything. A Pareto will always fit the data better, where it's significantly better is an issue, but it will always do it. Will it always do it better? Well, here it does it better. The 5%, so here you have to go to the tables. So we had to go to the chi-squared on 14 degrees of freedom, and if you do that, you find the critical value for a chi-squared on 14 degrees of freedom. 95 is 23.68. So the Pareto data does fit the data fine. If you wanted to do the final one, you have to go to a chi-squared on 13 degrees of freedom, and the 0.5 in this case is 25, and the chi-squared 13, the 1% one is 30.5. Oh no, sorry, I'm doing the wrong one here. No, this should be 15. So 15, so that is 25 and 30.5. So the chi-squared is occasional, it's larger than 25, it's 26, and it's less than 30. So 2 of those are right. Have people got the lecture to go to? Yeah. Okay. So this one here, I mean, what is the maximum likelihood estimate of a Poisson distribution? Well, you can do it, and it can be shown that it's the mean, and the mean is pretty obvious because mu is the mean, theoretical mean, and so the answer is B. 9. The important thing here is that the sum of 2 exponentials is going to be gamma with parameter 2 and a half, because this is the mean, so these exponentials are greater half. So it's going to be parameter 2 and a half, so the answer is A. Because we've got the lambda parameter here is a half, and we've got alpha minus 1 here. And there are 2 of those, so that's 1. 10. This is the moment generating, probability generating function, so if you differentiate it twice, you're going to get the probability x equals 2, but you've got to remember that it has this extra term, so the answer is D. So I kept saying that in the lectures, if you differentiate, it's going to be, you need to divide through by 2, differentiate twice and divide by 2 factorial, differentiate k factorial to generate the probabilities. This one here, well, we had to work out E of S, which is going to be the number of planes times, we have to see that that's a Pareto with parameters. It's a Pareto with parameters alpha equals 3, and let's call it lambda dash equals 4. So I'll give you the answer. And so that's going to be that times 4 over 2. We have to work out the variance of x and then do the sum. So perhaps I should tell you the answer. What was the answer? The answer in the end for this one was C. 12, you have to work out what is difficult, that you have to know that P of S equals 6 equals P of N equals 3. So the number of planes to get 6, S to be equal to 6, we have to have 3 planes. So once you can see that, then this is going to be from a Poisson with rate, what have we got here? 4. So that's 4 to the 3 over 3 factorial. So that gives the answer C. 13, where you have to, what is the mean of a translated gamma? Well, what is the mean of the gamma? Well, this is a gamma with parameters a fifth and 2. So the mean of the gamma is going to be 2 divided by 1/5. So the mean of the gamma is 10, plus the k is 10, so the answer is 20. So the important thing here is, this is the k you have to add on. The last two didn't require any calculations, so in a simple individual risk model, we assume the answer is all risks are independent and have no more than one claim allowed for the same risk. So the answer is C there. And the final one, we take out reinsurance to reduce the risk.